Yeah, that's good. Okay. So I guess we can get started. For the people who are here, was there anything in particular that you guys wanted to go over? I can't hear. Okay. Was there anything that you guys wanted to go over in particular? You can type it in the chat or say it out loud. Either way. All right, I guess if there's nothing, then we can kind of start from the beginning of the course. So if I'm not mistaken, you kind of start with the idea of a rate of change over an interval. So like here we have just a kind of like shape of a function. And we're taking the rate of change between these 2 points. So we have here, we have f of a, and then here we have f of b. But this isn't a great approximation of what the function is doing. But in any case, how we would calculate this is we would use this. We would do the value of the function at the larger or the second point in the interval minus the value of the function at the first point, and then minus the difference in the x value. So this can also be, you might have seen it as delta y over delta x. So the change in y over the change of x. But with that, we can kind of ask ourselves a few questions. Is this a really accurate representation of what the function is doing at like in general? And so if we kind of look at it, we see this green function has a lot more variation than this blue line does. So it's not that great of an approximation of what of the rate of change of the function. So maybe we can try and shorten the interval. So we can kind of consider an interval that has a change h. So this looks more accurate because this slope is looking closer to what the function is doing, but it's still not all that great. So using the formula that we had last time, we can do this. So we have the function like plus the difference minus the function at that particular value. And in the bottom, we have a plus h minus a. Now we know that simplifies to this. I kind of wish my keyboard wouldn't do that. So we have f of a plus h minus f of a over h. And so another thing that you probably talked about at the beginning of the course was this idea of a limit. So you kind of take points kind of getting closer and closer to a specific value, which doesn't necessarily have to be in the domain of f. And we write it like this over here. So we have the limit, or how you read this is that you have the limit as x approaches a of f of x is equal to L, where L is the value. So we can kind of use this idea of the limit to find the best approximation of the slope of the tangent line. And then also we'll compare that to what like the slope of the secant is. So slope of the secant is the average rate of change between 2 points. So like we had up here, this kind of idea, which you might have also heard it be called the average rate of change. And now we kind of bring in this new idea, which is the slope of a tangent, which is the rate of change at a specific point on a continuous function. Or you might have also heard the instantaneous rate of change. So we're going to quickly come back to this idea of the average rate of change on an interval. So what happens if we make that difference approach 0? So we can kind of take the limit as h approaches 0. But one of the ways that we evaluate limits is we just directly substitute the values into the function. But if we substitute 0 into the denominator, we can't divide by 0. So that's not quite going to work. However, as h gets smaller and smaller and smaller and smaller, we'll have our difference between the 2 points get smaller and smaller. Also, another note, it would probably be good to go over some of the limit laws. So like the sum of the limits is the limit of the sum and that kind of stuff, which is useful for evaluating limits in their own right. It's probably not, you probably won't see too much of it because it's not that big compared to what you do in the rest of the course. But this brings us to the idea of a derivative, which we'll go over here. So we have, what is a derivative? So we can find it in two different ways. We can find it at a point. So that is the instantaneous rate of change at a specific point A. Or we can kind of use the same idea of the limit, but use it to find the function. So instead of using a specific point A, we can just leave x in there, but still use this change h. And so then we define this to be f prime of x. So this will give us a formula for the instantaneous rate of change at any star point on the function. But any comes with a few exceptions. So you know that differentiability implies continuity, but we have continuous functions that aren't differentiable across their whole domain. So that's like poles or asymptotes. So an example with asymptotes might be like 1 over x, which goes like this and like that. So we can take the limit as x approaches 0, but we can't do it from the same side because these are going to two very different values. So that limit doesn't exist at 0. The left-hand limit and the right-hand limit do exist, but the regular, like both sides limit of 0 for 1 over x doesn't exist. We also have a second exception, which is these things called cusps and curls. So when we think of functions like the absolute value of x, we have on this one side here, we have the rate of change, where we have like the slope of this line is equal to 1. And then on this side, we have the slope is equal to -1. But what happens at this point? We can't differentiate that. There's also cusps, which are similar, but they're kind of just points like that. So they're not, they don't have like straight lines going to them. Differentiation has a lot of rules, which a lot of you will likely have seen in high school, but we can quickly run through a few of them. So for constants, so if we take the derivative of this constant a with respect to x, what will we get? So when we think about what a constant function looks like, let's do that. So we have y is equal to this constant a. There isn't a slope here. This is just a slope of 0. So, oh, that's the wrong one. Eraser. So we have that the derivative of a constant is going to be equal to 0. Another really handy one that you might have seen is the power rule. So we have that the derivative of x to the n is going to be equal to n times x to the n minus 1, which still works with negative exponents. So if we have 1 over x to the n, that's the same as 1 to the negative n. And so we can still use the power rule here. So we just bring down this minus n to the front, and then we'd subtract 1 from up here. And that just works exactly the same. So this can be proved using the binomial theorem with our limit definition of the derivative, which was up here somewhere, this one. Or we can use it with something called logarithmic differentiation, which I think I'm going to talk about later. But if not, it's a handy thing. Yeah. We also have this idea of constant multiples of a derivative or of a function. So if we take the derivative of this constant k times this function f, we can actually take that constant multiplier out. And that'll be the same thing as the constant times the derivative of this function f. So using our f prime notation that we had earlier, that will look like that. Another property with derivatives that we have is the sum of functions. So for the derivative of a sum, we also have the sum of the derivatives. Product rule is where it starts to get a little bit tricky. So when we have the derivative of a product, we have this formula where we'll have the derivative of the first times the second, and then the derivative plus the derivative of the second times the first. And then a little bit more complicated still, we have the quotient rule. If it kind of helps you to not get them backwards, or I know sometimes for the quotient rule, I mix up which one to do first. The product rule, I don't have so much difficulty with, but it's the same order, except you just have a negative here. So you have the derivative of the first times the second, minus the derivative of the second times the first, all over the denominator squared. Then another rule that you'll see used a lot is going to be the chain rule. So we have the derivative of a composition of functions. What we'll do here is we'll take the derivative of the outside function with the inside still intact times the derivative of the inside function. And then we also have a few handy derivatives. So we have that the derivative of e to the x is actually just the same thing. Okay, it's actually just the same thing. We also have that the derivative of ln, or the natural logarithm, is going to be 1 over x. And so now if we kind of extend this to just general exponentials, we have that the derivative of a base a to the x is going to be ln a times a to the x. So you might be wondering where this part comes from, because like where was it here? But we actually have that ln e is just equal to 1. So instead of writing out ln e here we just don't omit that. We just omit that because it's just a factor of 1. And then for over here, when we have the derivative of logarithm base a, we still kind of have that sneaky factor of ln a. But again, we have, so we have 1 over ln a times x. And so again, for here, when we would have ln e, which again is just 1. So we don't actually write that factor. The two probably simplest trigonometric derivatives are, so derivative of sine x is going to be cosine of x. And the derivative of cosine of x is going to be minus sine x. And so then let's say that you try to differentiate like negative sine again. You actually just get negative cos. So you can kind of think of it as like going in a circle, because once you differentiate negative cos x, you get sine x back. Or you can kind of use that idea of constant multiples and just take out, or yes, I'm not gonna. you can take out this factor of -1 instead. We can also find any of the other trig ratios using differentiation rules. So when we have tan x, that's just the same thing as sine x over cos x. And so for that, we can use our differentiation rules. And then you would get secant squared x, if I'm not mistaken, which is going to be 1 over cos squared. Yeah, and so you can kind of go through the other ones, like your secant and your cosecant and your cotangent. It'll be kind of the same idea. It's a good exercise sometimes. So now we're going to go through a couple examples of derivatives before we move on to integration. So here we have a function g of x, which is equal to the square root of 2x divided by ln of x. So here we have a couple of rules that we need to use. And so we'd have, this keyboard is really irritating. We'll have to use the chain rule, the power rule, and the quotient rule. But I know that might sound like a lot, but don't worry, we'll figure it out. So remember that we can kind of think of the quotient rule as d dx over, let's say, n of x for the numerator times the derivative of the denominator minus derivative of the denominator times the numerator. And then that's all over the denominator squared. So in this function, we have that our numerator is going to be equal to the square root of 2x, which we can also write as 2x to 1/2. And this is kind of where the power rule comes into it. So if we want to find the derivative of the numerator before we bring it all over into this quotient rule formula, we would bring this 1/2 down. So we have a factor of 1/2. And then times the inside function untouched, 2x. And then we have to subtract this, or subtract 1 from this exponent. So then we get -1/2. And then times the derivative of the inside function, which the derivative of 2x is just 2. So now we can kind of, so we have a factor of 1/2 here and 2 here, so we can kind of just cancel those out. And so now all we're left with is this 2x to the -1/2, which we can either keep with this negative exponent, or we can write it out again as a quotient. Then we also have our denominator. We have our denominator d of x is going to be equal to ln of x. And that's a derivative that we've seen before. So d prime of x is going to be just your 1 over x. So now let's use all these parts and we'll put them into our quotient rule formula. Or no, this isn't. That's not here. So we have that, which is d dx of this dx. And so let's start summing some stuff in. So we have for our numerator, we have 2x to the 1/2 times the derivative of our denominator, which we found to be 1 over x, minus, oh no, this isn't prime, this is prime. So you have the derivative of the numerator, which is going to be our 1 over 2x to the 1/2 times our numerator, which is going to be ln x, minus the derivative of our denominator, which is 1 over x, times the numerator, which is going to be 2x to the 1/2. And then this is all over ln x squared. Now I'm going to give us some more space. Let's try that. Since we've got some quotients in the numerator and we also have denominator, it might be a little bit easier to think of it as multiplying two fractions. So here we have 1 over ln x all squared times, let's simplify these fractions a little bit. We have ln of x over our 2x to the 1/2 minus, then we multiply this out as well, and we'll get 2x to the 1/2 over x. And we could simplify further than that. We don't really need to necessarily, especially on a final or a midterm, really any kind of timed assessment. Unless they tell you to simplify as much as you can, you don't have to completely simplify everything because, again, you have limited time and simplification can take a lot of time. But yeah, does anyone have any questions about this process with with a bunch of derivative rules in it? Is that okay for everyone? I'll take that as a yes. So in that case, we can move on to this second example. So here again, we'll have multiple rules because here we see like a function with a function on the inside, and then we've got a product of functions. So we'll have, once again, 3 rules that we have to use, which might sound intimidating, but it doesn't need to be. So let's think about what we would need here. So for the product rule, so for this d dx f of x, we'll take, let's call this one big F of x for first, and then s of x for the second. So we'll have the derivative of the first times the second plus derivative of the second times the first. And then we'll start working out these bits on the side here. So for our first function, we have 3x to the 5, which that's just a kind of run-of-the-mill power rule. So we bring down this exponent. So we have 3 times 5, which is going to be 15. And then we subtract 1 from the numerator here, which is going to be 4. So then that's our derivative. And then for the second one, this one's a little bit more complicated. We have 6x to the 4 plus x all to the 4. And so this is kind of where the chain rule comes in. So we have this to the 4. So we bring the 4 down. And then we keep our inside untouched. And then subtract 1 from this exponent. So we get 3. And then times the derivative of this inside part. So then we have, I guess, kind of 2 power rules. So we multiply this 4 by the coefficient on x. So we get 24x, then subtract 1. 24x cubed plus the derivative of x is just 1 times 1. And so that's going to be the derivative of our second one. And so now we just plug that in over here, and we'll get 15x to the 4 times 6x to the 4. Don't know why that kept writing. 6x to the 4 plus x, all to the 4, plus our s prime of x, which is this whole guy here. plus 4 times 6x to the 4 plus x cubed times 24x cubed plus 1. And so again, we could leave it like this. A pretty easy factor to pull out would be, here we have 4 of these terms, and here we have 3 of them. So you can bring those out to the front. 6x to the 4 plus x cubed, and then we have the rest of it in here. 15x to the 4 times the 1 factor of this that's left. So 6x to the 4 plus x plus, and then all of these came out to the front. So we have 4 times 24x cubed plus 1. On an exam, not really worth it to try and expand all of this and collect all your like terms. You're going to get massive powers of x, and if you're just trying to calculate the derivative, that's not super necessary. But yeah, does anyone have any questions about this chain rule, power rule, or product rule question? Do we need to multiply by f of x as well? Yes, we do. You're absolutely right. So, and we'll get rid of this for a second, and we'll just take all of this a little bit to the side. Thank you, Marina. We'll move all of this over. Move all of it over a little bit. And so then I did forget to multiply by f of x again. So then we have our 3x to the 5 here. And so then we can still take out this common factor of 6x to the 4 plus x. And then on the inside here, we'll have 15x to the 4 times 6x to the 4 plus x. This is just to the 1. Plus 4 times, this got all the, this moved out here. And then 24x cubed plus 1 times our f of x term, which is 3x to the 5. Yeah, thank you. All right, any other questions? Alrighty, I guess we'll move on. So another big, I guess probably 2 of the biggest topics in this course, you have applications of derivatives and you have integrals. So before we move on to integrals, we'll keep talking a bit more about applications of derivatives. So some ways that you might see this is that you might see something called implicit differentiation, which is where in the same function you have terms of x and y, but x is, I guess, you can call implicitly defined. So it's actually a function in terms of x. And so the way that we go about doing this is that we would differentiate the whole expression, both sides of the equal sign with respect to x. And then when you need to do a derivative for y, because that would be technically the chain rule, you write this term dy dx. And then once you've got all those terms, then you isolate for your dy dx, and you'll get the derivative of y with respect to x. This is really the strategy that you want to use for any related rates questions. So you might have changes in volume with respect to changes in one of the sides, or really common questions like that are the ladder ones. So you have like a ladder up against a wall and it's sliding down at this rate, and you want to find out like the rate of something else with respect to that triangle, especially for those ones that you want to use the Pythagorean theorem and this, and like this change in y over the change of this axis. But yeah, another kind of application for derivatives is finding the equation of a tangent line at the point A. So for that, if you kind of think about, we had this sort of green curve at the beginning, like this. To approximate this function at a specific point, so let's say this guy right here. So we'd want to find the equation of the line that is tangent to it, like that. So this linear approximation formula gives you f of x is approximately equal to L of x, which is you evaluate your function at the point A, so you get this value, plus the derivative of the function at this point times x minus a. And I think that was all I had for applications of derivatives right now. We'll probably come back to it at the end with a curve sketching example, because that uses a bunch of derivatives. But really the biggest part of the course is integrals. And so now we talked about derivatives, but an antiderivative kind of goes the other way. So we have an antiderivative called capital F of x. This is a function for which its derivative, capital F prime of x, is equal to just this function little f of x. So kind of thinking about the connection to, like, for that between derivatives, if we have that capital F prime of x is equal to cosine x, what might f of x be? And so for that, we would have sine x. Another example that we might have, so say f prime or capital F prime of x is equal to e to the x. What might its antiderivative be? So like what function do we take whose derivative is equal to e to the x? Now, because e to the x is a nifty little function, we have that it's also just e to the x. Another thing we might have is a polynomial function like this. So if capital F of x is equal to 2x, what could we have differentiated to get 2 to the x? And so for that, we have just x squared. This keyboard is really irritating. And so now also another one. If we take capital F prime of x is equal to 0, what could f of x be? Yeah, of course. I'll make them into a folder, and then I can, if you want to send me your email at the end, I can email them to you. I can make them into PDFs, whatever's easiest. But yeah, I'm happy to send them out. But yeah, so if we have this, no problem. So if we have this capital F prime of x is equal to 0, what could f of x be? And so we don't have a super specific answer like the other ones. We actually just have that f of x would be some constant c. We don't know which constant, because every constant differentiates to 0. So that's kind of when we write it out as an integral. This constant of integration, this plus c, is super important, because that we have no idea without, like, unless we have a specific condition, what the constant attached to this antiderivative could be. So when we write out an integral, we start with the integral sign here. And then at the end, we always have this dx or d, whatever variable we're using to, like, what that we're integrating with respect to. So like if we had a function that was like, I don't know, sine theta, the variable that we're integrating with respect to is going to be theta. So we have d theta at the end. But this d variable and this integral always come together. So you always have to have both of them. This one's a little bit easier to forget. And then the spin on the inside, this f of x, it's called the integrand. And that's what we're trying to integrate to get our antiderivative capital F of X. So some ways that we can go about integrating would be to kind of undo some of our derivative rules. So like when we have 0, when we kind of undo that, we get a constant. Or if we just have a constant in this integral, then we get kx plus our constant c. But then if we differentiate this, so if we differentiate kx plus c, this c turns into 0. But then we have our biggest kind of power. We have our x to the 1 sort of. So this 1 gets multiplied by k, and then the exponent on this x, we subtract 1. But 1 minus 1 is 0, so we'll get x to the 0. But x to the 0 is just 1. So all we're left with is k. Put that over to the side a little bit. Clean that up faster. Another pretty easy one that we can sort of undo is just a exponential term with an x in the bottom. So when we think about the power rule, remember we multiply down from the exponent and then we subtract 1. So for this one, we have 1 over n plus 1 times x to the n plus 1. So then if we think about like trying to differentiate this part, we have n plus 1 times 1 over n plus 1. That's just 1. So our coefficient in front of the x is just 1. And then we have n plus 1 minus 1. So that's again just n. And then our constant of integration, super important. Before I went into my calculus 1 midterm, I wrote plus c on my hand, which might technically be cheating. So I don't know if I recommend doing that for you. But it's super important that you don't forget this plus c, because that's one of the easiest marks to lose. One particular case of this, though, is when we have n is equal to minus 1. So kind of come over here for a second. And so let's say we have our integral of x to the minus 1 dx. So another way that we can write this would be the integral of 1 over x dx. And so then if we try to use this kind of undoing the power rule formula, we have, we'll use this one. So here we multiply 1 over n plus 1, but we have that n is equal to -1, so then plus 1, and then we have x to the -1 plus 1. And here we're going to get 1 over 0, and then it doesn't matter what we have over here. This simply does not work. Although you might recognize this guy here was a derivative that we saw, one of those handy ones. And so this integral is actually just equal to 1 of x plus c. But yeah, so that's a little side note, something to watch out for. Integrals have some of their own kind of neat little properties. So again, when we integrate with a constant attached to a function, we can take out the constant. This helps to make derivatives a lot simpler sometimes, or integrals a lot simpler sometimes. We also have that the sum, or the integral of a sum, is the sum of the integrals. And this is equivalent for a difference. I'm not sure if this is something people will have seen before. Those are equivalent. So now we have a couple of other derivative rules. And what do we do about integrating things that are a little bit more complex? So sometimes we have an integrand that looks like we might have applied the chain rule to it. So let's take, for example, this integral of 2t times e to the t, or e to the t squared dt. So what could this antiderivative have been? Here we use a technique called u substitution, which is one of my favorites. I still use it in my calculus classes. And so the kind of general strategy is we'll set the inside function to be just a variable u, but what it's actually doing is a function in terms of x. So, for example, here we would take u is equal to t squared, but then remember that when we have a function, or we have a function, we still have to multiply by the derivative. Or when we have a composition like this, you have to multiply by the derivative. So we'd have du dx, which is just, or in this case, we have t. Put t here. Du dt is equal to 2t. But then we only want things in terms of u right now, so it makes it a little bit easier when we go to substitute it back into our function. So we have du is equal to 2t dt, like that. And so now if we do those substitutions, we'll get this integral, which looks a lot simpler. We have the integral of e to the u du, and that's something that we've definitely seen before. So then we integrate that, and since e to the x to the u, that integral, we just have e to the u plus our constant of integration. And then we could substitute what we had for u back in. And so we just get e to the t squared plus c. Does that make sense? Are there any parts that are confusing about that? I'll take that as a no. So we'll move on to our next little strategy. Sometimes you might see a product in your integrand. So here we have the integral of x e to the x dx, which doesn't look quite like the chain rule, because like this, the derivative of this part up here is not x. So here we would use a technique called integrating by parts, which might be a little bit time consuming, but it's very useful. And so our general strategy when it comes to integrating by parts, so we choose the components of your product in your integrand so that you can calculate the derivative of one easily and the antiderivative of the other part easily. So a little bit more specifically, for integration by parts, we have the integral of u dv is equal to u times v minus the integral of v du. So here I have all of the u terms in red and the v terms in orange. So since here we have u, which is the same thing, and then a du, we're going to want to take our u so that it's a little bit more easily differentiated. And here on this side, we only have a dv, but on this other side of the equal sign, we only have v's. So there, it'll be important to find something that we can easily find the antiderivative for. So kind of moving on to this next part, which should we choose for u? Which will be the easiest to differentiate? And which should we choose for v? Which one's antiderivative would be simpler? So here we have our x times a to the x dx. So now we're going to choose u to be x because that derivative is super easy. And if I can highlight it properly, there we go. We're just going to get 1. And that's a really easy derivative to use because it doesn't really have any impact or have a lot of impact on other things. And so that means for v, we're going to choose e to the x. And so sometimes it might be, you might have that the easier one to differentiate is e to the x. But in this case, when we have an x term, that just goes to 1, and that's even simpler to use. So then moving on to using our integration by parts formula, we have x times e to the x minus the integral of e to the x times 1 dx. So here we have u times v minus the integral of v du. And so then e to the x is something that we can really easily integrate. So then what we're left with is x times e to the x minus e to the x. Actually, a pretty easy simplification you could do for that would be e to the x, and then you have an x minus 1 here. Does anyone have any questions about integrating by parts? Does that make sense? How do you know if you've chosen the right u? So when you're integrating by parts, you don't, kind of a tip or like something that should tip you off to maybe that you've chosen the wrong ones is that this integral is more complicated than what you had over here. That's usually a good sign. Although this might happen a little bit more in calculus too, but it's not uncommon that you might have to do integration by parts twice. So you get this part, which makes sense, and then you have another integral over here. And that's still something that you have to do by parts. So you'd have to do it all over again. And then kind of do this integration by parts, maybe over on the side somewhere, and then substitute what you get for your formula over here, the du back into this one. Marina's prof gave us the IEEE strategy. For you, the order of importance is I inverse trig functions, L logarithms, A algebra, so like not trigonometric functions at all, polynomials, T trig functions, and E exponential functions. That's actually, yes, that's a good strategy. That's something my professor, when I took this one, didn't share that with us. But I definitely know other sections did have that. Did share that as well. Their prof said logarithms first and then inverse trig functions. Yeah, it really just kind of depends on what inverse trig functions and logs are both a little bit more on the complicated side to try and integrate. So kind of either of those, whichever you feel most comfortable differentiating, you can use from here. But yeah, one of the biggest hints that you've maybe not chosen the right u would be that your second integral here is just as complicated or even more complicated. Does that help? Yeah, awesome. Yeah, so then I'm moving on to the next one. Sometimes we have powers of trig functions. So for example, here we have sine cubed of x dx. You can also have, like, I guess a more general form of this kind of example would be sine to the m x times cos to the n of x dx. So in this case, you'd want to, like, for odd powers, you want to save one factor. So if m was odd, you'd want to save this one sine of x, and then have the rest of your sine of x terms, sine of m minus 1 terms here, and then your cos terms over here. Pretty messy, but and then you're going to use the Pythagorean identity. Now, if that sounds long and scary, I promise it's not. It's my absolute favorite trig identity, and it's probably one of the most helpful ones. So in particular, we have cos squared of x plus sine squared of x of x is equal to 1. And so then we can rearrange this sometimes. So if we want to get cos x by itself, we have 1 minus sine squared of x. And then once you do that, once you get your even powers, you want to do u substitution. And then if you already just have even powers, you want to use your half angle formula, which I think I mentioned a little bit later on. But yeah, so for this example with sine cubed of x, we have an odd power of sine, so we want to keep one of the sines by itself. And then here we'd have our sine squared of x. But we're gonna turn this into 1 minus cos squared of x. And then for our u substitution, we're gonna take cos of x. And we're gonna have our du is equal to sine of x. And so we're gonna be a little bit clever here, and we're gonna keep our du and our negative sine x in the bottom, because then this sign here and this sign here are going to cancel. And so now you're just left with the factor of -1, which you can bring here. And then this is a polynomial that you probably have a better idea of how to integrate. And then when you've got other, like say you have other cos terms here, these are just existing out here, and you'd still use them for u substitution. And instead you just have u to the power of something. And then I'm pretty sure that's something that you can do as well, that you have the tools to do. So then in this case, with an even power of cosine, again, we want to get our squared factor, or we want to keep it in terms of squared. So we'll take out with the factors. So here we have the 4 is equal to 2 times 2, but say this was a 6. We want to have our cos squared of x in the middle, and then times the other power out here. Yeah. So then we would use this as our as our half angle formula, which is going to be this guy here. And then you would continue with substitution as well. Next up, we have another strategy called trig substitution. So that's where we're trying to get something that is square underneath a square root. So for example, here we have the integral of the square root of 1 minus x dx. And so again, we remember that we have 1 minus cosine squared of x is equal to sine squared of x. So here, we're going to substitute in for x sine of x, or sine of theta. And then that means that our d theta is going to be cos theta d theta. So then we bring that back over here. We have 1 minus our sine squared, or sine theta all squared, which then we can use our Pythagorean identity over here and bring this as cos theta. Or yeah, we'll have cos squared theta under the square root, and then we'll square root cos squared theta. So then we get cos theta times cos theta times d theta. And then we remember what we do for even powers of trig functions. We have our half angle formula, which we'll substitute back in. So now we're left, we have a 1 over 2 times 1 plus cos of 2 theta d theta. Now this is something that we can probably do a little bit more easily. We can break it apart if you want, and have our 1/2 d theta, and then our integral of 1/2 cos 2 theta d theta. In any case, either way, you're going to be left with your integral, which is going to be 1/2 theta plus 1/4 theta sine of 2 theta. And so now we think back to our double angle formulas for trig, and we have that sine of 2 theta is also equal to 2 sine theta cos theta. And then we remember the substitution we did where we had x is equal to sine theta. And so then that means that we have theta is equal to the inverse sine of x. So then we substitute that in here. And here we have cos theta, which if we, again, bring back our Pythagorean identity, where we have 1 minus cos squared theta. Where am I going with this? If we have cos theta, that's going to be, oh yes, here we go. 1 plus sine squared of theta. And then we have x is equal to sine. So then we have our square root of 1 plus x squared. And then using these handy little things, we substitute our functions in terms of x back in, and we're left with 1/2 of the inverse of sine plus 1/2 x times the square root of 1 plus x squared plus your constant of integration. So trig substitution is one of the trickiest ones. So if this seems a little bit convoluted, it kind of is. I don't blame you for thinking that. It's definitely something that you kind of have to be aware of and kind of have to keep an eye out for. But then this is a little table of, so if you see these expressions over here, that might be kind of like a little hint that you might need to do trig substitution, or that you will have to do trig substitution. So when we have the square root of 1 minus x squared, we're going to use this form of the Pythagorean identity. So 1 minus sine squared theta is equal to cos theta. So the substitution that you're going to do here is going to be x is equal to sine theta. And then these restrictions on theta are important because if you're doing trig substitution, you're going to have an inverse term somewhere. And the inverse of trig functions is only defined on a certain domain, or on a certain like interval. And so here we have the square root of 1 plus x squared. And here we're going to use this identity here that we have 1 plus tan squared of theta is equal to secant squared of theta. And so the substitution that we're going to do here is x is equal to tan theta. And then again on the same interval for theta. If you're kind of wondering where this one came from, that's because tan x is sine theta over cos theta. So if sine theta is only defined on this specific interval for its inverse, then tan theta also has to be. And so then over here we have the square root of x squared minus 1. So we're going to flip around this identity. We're going to get secant squared of theta minus 1 is equal to tan squared of theta. And then so for that substitution, we're going to be using x is equal to secant theta, which is only defined on these ranges. So 0 to 2 pi, or pi to 3 pi over 2. Does anyone have any questions about that? How would you integrate something with two functions? So if you had cos cubed of x times e to the sine x. That's a good question. And I think that would just be a gigantic integral by parts, because you have a product there, two things that aren't really related in terms of like maybe the chain rule or something. So for this first half, or for one of the parts, you probably have one that's a little bit easier to differentiate than the other. So I'm thinking maybe e to the sine x might be a little bit easier. than cos-cubed effects. But then I think you'd have to go through a giant integral by parts process to do that. If you do have something like that on your final, the advice that I would kind of give to you would be try not to let little things slip through the cracks. So try to really make sure that you're not forgetting anything. But also, if you have like the big integral by parts thing, I always find it helpful to do the kind of smaller parts on the side. So kind of like we did for the derivatives when we did the chain rule on the side before putting it into the quotient rule. I find that that kind of helps me to keep track of stuff like that. I hope that helps. I don't know how I would do that off the top of my head. But yeah, if you're curious right now or shortly after this, I might suggest putting that into something like Symbol Lab or Wolfram, to be honest, because those, even though they don't show you all the steps if you don't pay money, they'll usually tell you the kind of general strategy that you have to use for them. I hope that's a little bit helpful. But yeah, sometimes big things like that are good practice. So using like multiple different rules at the same time to kind of make sure that you understand the way that all the parts fit together could be helpful. But then kind of on the flip side of that, sometimes trying to come up with your own questions kind of gets you a little bit stuck sometimes. But yeah, if you're curious about that, I would say probably try and find a calculator that would give you maybe the general idea for some steps. But yeah, does anyone have any other questions? All right. So then we'll move on to partial fractions, which I actually did not have a chance to go through entirely. So I think we're going to go through it together now. Integralcalculator.com. I don't know if that's one that I've used before. There's a whole bunch out there. I think the ones that I've used most commonly are Symbol Lab and Wolfram. But yeah, there's a whole bunch out there. So the idea of partial fractions. Before we get into this integral, I'm just going to talk a little bit about the idea of where partial fractions comes from. So here we have a denominator that is larger than our numerator. So here we call this a proper rational function because the degree of the denominator is smaller than the degree of the numerator. In the case where you had the opposite, that the numerator was larger than the denominator, you have to go through long division in order to get something that maybe you can take a factor out of, or maybe you get a bit of a gross division. But that's how you'll be able to integrate that. Just you'd have to make sure, if you wanted to like choose partial fractions, you'd have to make sure that that your degree of the numerator is smaller than your degree of the denominator. So for this particular case, we're fortunate that we have a denominator that divides or that factors nicely. So here we have 2x plus 3 all over x plus 2, x plus 3 dx. So now to find what two numerators we had when we put this over the same common denominator, we're going to use these two fractions here. We have a over x plus 2 plus b over x plus 3. So we're going to just kind of come back to this integral in a minute. So here we have that 2x plus 3 over x plus 2 times x plus 3 is equal to something over x plus 2 plus another something over x plus 3. So now we know that, like, if we expanded this, that we would get the same denominator as over here, and then we'd get this numerator. So we can kind of just get rid of the denominators for a little bit, and then we'd have that 2x plus 3, or if we were to put these over, if we were to common denominator these, we'd have that we get ax plus 3 plus b x plus 2. And so now we'd expand this side over here. We'd get ax plus 3a plus bx plus 2b. And so now over here we have a polynomial which has an x term and a constant term. Here we have some constant terms and some x terms. So let's group them together. So we'd have, let's have ax plus bx, and then we take 3a plus 2b, and now we can we'll get a plus b times x plus 3a plus 2b. So like this is going to be our constant term. And so now we can kind of get this system of linear equations. So I don't know how many of you guys are in linear algebra right now, but you can set it up as a system of linear equations. So you have so you could set it up sort of like a plus b is equal to 2, and then 3a plus 2b is equal to 3. And then your kind of ultimate goal would be to write one of the equations in terms of the other variable. So for example, if you wanted to get a by itself, we have a is equal to 2 minus b, and then you substitute that in here, and then you have an equation in terms of only a's, or no, an equation in terms of only b's, and then you isolate for b, and then you put the b back in here, which is a little bit complicated. Or you can kind of like choose some kind of smart ideas for variables. So in our case, we could try 3 is equal to b. So if we put that in here, then we have a is equal to 2, and that gives us that a is equal to -1. And so does that work for the other one? So if we have, that's not a 3 at all. We have 3 times -1 plus 2 times b, which we said was 3. What do we get? We get -3 plus 6, and that's also equal to 3. So then kind of using those smart choices for our system here, we now have our numerators for this part. So we have that 2x plus 3 is equal to, we'll get -1 over x plus 2 plus 3 over x plus 3. And so now that is something that we can substitute back in here. So we'll kind of just take this linear system off to the side over here somewhere. And then we'll move this over here a little bit more. Maybe like that. And then now we'll come back to this integral, which I'm just gonna like come down here a little bit, so it's maybe a little bit less cramped. So we have 2x plus 3 over x plus 2 times x plus 3 dx. So that's going to be the same as, I'm going to just switch these around a little bit just because we have a negative here and sometimes it's nice to have the positive term be at the front. So then we'll have 3 over x plus 3 minus 1 over x plus 2, and then again dx. And so if we think back to some of our properties of integrals, we have a difference of 2 terms, so then we can make that into 2 integrals. 3 over x plus 3 dx minus the integral of 1 over x plus 2 dx. And so what also, just to be like super clear, this negative that is out here, it's kept here. So kind of just took the integral of that. Kind of another way that you could think about it, I guess, if you really wanted to, would be thinking about this as a whole term, and then this is the addition of a negative number. So then you have your integral of this first part, which I'm going to do as a star, and then plus this integral of another thing, which I'm going to do a square for with a minus up front. But then we also have the whole constant multiple thing, so we could take this negative out, and then we're left with the same thing as we have down here. Uh-oh, there we go. That's not the eraser, it's the eraser. Alrighty. And so now these are some things that you would have likely seen. So we'd have this rational is going to be equal to 1 of the absolute value of x plus 3. Again, we have a plus c here, minus value of x plus 2. Again, plus another c. But since we have 2 c's that we don't know what they are, we could put little subscripts on them if we wanted to. We don't have to, because again, we still don't know what they are. Or we can just kind of like squish them into one constant of integration for this whole thing, plus c, which is these 2 constants just added together. Yeah. So that's a partial fractions question. Does anyone have any questions? Anything that's a little bit confusing? Is linear algebra something that you guys are in this semester? Or is that a winter class? I forget. Winter, okay. Then maybe some of you guys, oh, both, okay. Oh, fair enough, okay. Since some of you will have seen this idea of a linear system, I guess you might have also seen it in calculus and vectors in high school if you took that. But kind of this idea is you have 2 equations just in terms of different variables of x. So here we'd have like ax. This is going to be the same x plus e times that same x is going to be equal to 2. And then down here we could say we have x with sub-0, which we could say is just 1. But you're kind of just, it's maybe a bit of a simpler way to write out a bunch of equations that have the same variables in them. But yeah, so if you had not seen it, or maybe if you are not quite sure what kind of clever values to take for your variables here, probably the way that I would go about doing this, like I said, I'd isolate for one of them, and then this second equation here, we can turn this 2 into, I think the session is going to be shared somewhere. Okay, I think you said it'll be on YouTube. But I'm also gonna, if you would like the notes afterwards, you can send me your email, or like I'll collect your emails at the end if you'd like to see the notes, or keep them after the session. But yeah, so kind of start this for the strategy for this one, you'd want to get a by itself, so then you have this other function which is just in terms of a and b, so then you can substitute this little expression for a, get 2 minus b plus 2b is equal to 3, and then 6 minus 3b plus 2b is equal to 3. And then let's subtract 3 from both sides, and we'll get 3. And then if we add these two together, we'll get negative b. So let's add b to both sides. So then we get 3, b is equal to 3. And then you just substitute this value for b back into your first little equation there. And that's kind of how you do that as a linear system. I'll write that out in a little bit more details afterwards. I'll kind of clean up the notes a little bit before I send them to you guys. But yeah, and I guess the last thing that I wanted to go over would be curve sketching, which I mentioned a bit earlier. It's a bit of a process. I would not be shocked if they asked you a curve sketching question on your exam. And some of you guys might not have actually covered this in class yet. I know in particular, Professor Malta's session is, I think, doing this tomorrow. But in any case, you may have seen it. It might be good to see it multiple times. So we're going to take this function f of x is equal to x plus 2 squared, x minus 1. Oh, actually, but before we do that, that reminds me. That's not this. That's not the lasso. If you have in your denominator a function like this that has a multiple term, when you set up your partial fractions, you're not going to have two of the same term. What you're going to do is, so let's say actually we had this as the denominator for our partial fractions. We would take a over x minus 1 plus b over, then we'd take x plus 2 with no exponent, and then we'd take a third term, which I think would still just be c on the top, and then you would take x plus 2 squared. Now when you expand this, this might be a little bit more complicated, a little bit bigger. Again, a little quick thing, this might be a cx plus d here because of the exponent here, but I'm not 100% sure. I would say double check that before you start trying to maybe do a partial fractions like this. But yeah, so just a quick note about that. So now on to curve sketching. This is really fun because this equation is already factored. So that means it'll be really easy to find the roots. So in particular, we'll have two roots. We'll have x is equal to -2 and x is equal to 1. So these are going to be where your function passes through the x-axis. I'll put in a little grid at the end. But once we have our roots, we can also find, I guess we don't really need where the function will cross the y-axis right now. So now the first thing that we're going to do is we're going to take our first derivative. So that's just going to be your first f prime of x. And so like we had earlier, this is going to be a product rule because of these two guys here, but also a chain rule because we have this squared up here. So remember our product rule is we have the derivative of the first times the second plus the derivative of the second times the first. And so for our first one here, we have that the derivative is going to be, we have that f prime of x is going to be equal to 2 times, then the inside is untouched, then this exponent, we subtract 1. So that's there would be a 1 here, but you don't really have to write that because that's kind of the same thing. Times the second. So then we have x minus 1, and then plus the derivative of the second part, which that's just this goes to 0, and this turns into 1. So we have a 1 here times the first one. So then we get x plus 2 squared. So then we write that back over here times x minus 1 plus 2 squared. And so then the next thing that we have to do is find where our first derivative is equal to 0, because that's gonna give us the points where our function either goes from increasing to decreasing or vice versa. So this expands to a quadratic. So let's do that really quick. So we'll have this 2 times x plus 2, x minus 2. So we have x squared plus 2x minus x minus 2. And then plus we have this nice perfect square over here, where we'll get x squared plus 4x plus 4. Then we collect our like terms, and that's a squared. We'll get a 2x squared plus x squared plus 4x minus 2x is just going to be 2x, then minus 4 plus x squared plus 4x plus 4. Then again, we group our like terms. We get 3x squared. No, we don't get that. That's not quite the case. So we're going to do that in a little bit fewer steps. We're going to expand this 2 first, and then we'll group our like terms. So we get 2x squared plus 4x minus 2x minus 2. And then this is just a coefficient of 1, addition, plus x squared plus 4x. 1 second. Yes, you're absolutely right. Thank you. The 2 expanded, or the 2 distributed to here would be a minus 4. And then we have a plus 4 here. Do we actually have all of the? And then so we group our like terms. We get 3x squared. Then this is 2x plus 4x is going to be 6x. And then we have a minus 4 and we have a plus 4. So that's just 0. And so then we find the roots for this guy. We can take the 2 out, or we can actually take a 2x out. Even better, we can take a 3x out. 3x, and then we have x plus 2, which means that at x is equal to 0 and x is equal to -2, we're going to have critical points. So we're going to have where the function goes from increasing to decreasing and decreasing to increasing, but we don't know which one yet. So one of our first steps is going to be to, actually, we have to calculate the second derivative first. So we're going to take this function and we're going to differentiate it again with respect to x. So for f double prime of x, we're going to bring the 2 down, so then we get 6x plus 6. And so that is the same as this, which is only equal to 0 at 1 point, and that's going to be x is equal to -1. And so when the second derivative is equal to 0, that corresponds to something called a point of inflection. So that's where, so it'll still be increasing, but we might have that it goes from concave up to concave down. So like concave up would be like a parabola like this. Concave down is again, well, the opposite. So we have this way. But a point of inflection, so here we have this part is concave up, but this part is concave down. And so that's what happens when your second derivative is equal to 0. So now that we have all these points, we can make this fun little table, which is going to tell us what the function's behavior is around these points. So we're going to have an interval from negative infinity to our smallest one, which is -2. And then we have at -2. And then we have our second interval, which again, talking for the song is kind of making my throat dry, which I guess isn't that shocking. -1, and then we have at -1. Then we have our third interval. Actually, do you need to do 2 tables or is this just 1 table? Actually, I think we can do 2 tables. So we'll do the first table to find out where it's increasing and where it's decreasing. So for that, we'll only use these 2 here. So we'll take our first derivative here. And so we'll have the interval from negative infinity to 0. Then we'll have at 0. Or here, we're building this table out of the roots from the first derivative. And then we are going to have no, that's also incorrect. Our first interval is going to be from negative infinity to -2. And then we'll have the value of the function at 2. And then we'll have the interval between these 2. So we'll have -2 to 0. And all of these are open intervals. So that means that -2 is not included in this one. If it were included, which would happen in a different context, you'd have, say, the open interval from negative infinity to 2, and this closed bracket means that 2 is included in this interval, whereas this means that it's not. And so we have this second interval. We'd have the function's behavior at 0, and then we'd have our 0 to positive infinity. And then we'd make this into a fun little table. Maybe like that. And then what we're going to do is we're going to take a value from each of these intervals and substitute it into the original function. So if we bring it back down here, we have that f of x is equal to, it was x plus 2 squared times x minus 1. Yes. Okay. So when you're doing these intervals, you always want to take the simplest values that you can. So for this interval here, I'm going to take -3. Not the most simple, but better than a fraction. And so here I'm going to take -1. And then on this one, I'm going to take 1. And so now we sub -3 into this. We're going to get 1 squared times -3 minus 1 is -4, which gives us -4 here. Next, we're going to do with our -1. So again, we're going to have a positive 1 here this time, squared. And then we're going to have -1 minus 1, which is going to be -2. And so that's going to be -2 here. And then on this interval, we're going to take 1. Did I get this backwards? No, I did not. Then for this one, we're going to take f1, and then so then we have 3 squared times 0, which means the function is going to be equal to 0 here. And then we're going to sub in -2. We're going to and we substitute in 0. And this is not making sense. I will, instead of continuing and doing this probably incorrectly, I'll write it out on the notes and then I will send it to you. But since a lot of you will probably be doing this next week in class, it's not the end of the world if I don't finish it, because your professors will probably explain it to you a little bit better than I am right now. So with that, does anyone have any other questions? Not necessarily about this, about anything that maybe I've talked about before earlier, other things in the course. Wait for a little bit. All right, I guess if nobody has any, from my experience, how was the final for Calculus 1? It wasn't too bad. It was one of the first exams that I wrote in university, which was a definite jump from the exams that I wrote in high school. Actually, I guess you guys will be writing this final in person, which is what I also did. So the content of the exam wasn't too bad. Since all of this is kind of different extensions of the same idea, a lot of it's probably going to be fairly related to to the other questions, or they won't be too far off, is more what I'm saying. Definitely do a lot of integration practice, do a lot of derivative practice, because again, that's really the bulk of the course. But the content of the final wasn't too bad. Really, the biggest thing for me was writing in a massive gym with hundreds of other people, which was not fun, but it's kind of a quintessential university experience.
Just one thing I'd like to add. When I wrote the class, the professor provided me with a lot of example questions, and quite a few of those appeared on the final exam. So if your professor provided you with some sample questions, I would definitely recommend preparing those.
Yeah, I know some professors who straight up their practice finals and practice midterms are this exact same questions that are on the exams, but with the numbers changed just a little bit. So definitely, if your professors give you a list of topics that they say will be on the final, focus on those, but don't kind of leave the other stuff to the wayside just in case. But yeah. I'll try and have the notes finished or cleaned up by later today. So hopefully those can be out by Monday. Yeah, we'll say Monday for the video and the notes. Anything else? Yeah, no problem. I guess if nobody has any questions, we can kind of call it there. If you guys, I guess, have any other questions, I'm in the site Discord. You can find me as Sophie-WIE chair. So if you guys are really stuck on something, you're more than welcome to ping me and I'll give you a hand. Yeah. I guess have a good rest of your day and good luck on your exam. Yes, in the big site Discord. You can find me there. If any of you guys are in the math server, I'm also there, but it's just so. But yeah. Oh yeah. So Stefan sent an invite to the site Discord. Sweet. Okay. Any other questions? Any other concerns? Yeah, I'm glad, of course. All right. Yeah, of course. Take care. You too. Alrighty.